Good choice. Okay, find the sum of infinite geometric series. We're going to look at this classic paradox from the Greek philosopher Zeno. We're up here. Thank you. Zeno shows the doors to truth and falsity. Spanish students, help me out there.
100.
Veritas. Falsitas. I think that's Latin, actually.
Yeah.
That's a minotaur.
Yeah, it's lies.
And falsity. That's a minotaur.
So to get across the door, Zeno here has to first get halfway across the hall, right?
Yes.
That will take a finite amount of time. And then he cuts the distance in half. That will also take a finite amount of time. And he keeps cutting the distance in half and adding up all those infinite collection of finite bits of time, which he reasoned that would be an infinite amount of time. So it takes forever to get to the door. Okay?
Oh, that's like what.
So you can't get there. But if he doesn't think about it and just does it, he gets there in a finite amount of time. Okay? So here's where his paradox comes into play. If we view it, though, as subdividing into a half, plus a fourth, plus an eighth, plus that infinite series, he thought that that then would be an infinite amount of time. Well, how do we resolve this paradox? Give me some ideas. Because we know it's one all the way across the hall. One width of the hallway. One all the way across.
I'll just take one.
It'll get within a million.
Oh, you mean, but you're saying it'll never get there.
But it will get there.
No, it will never get there.
Isn't it like that thing that gets
We'll never get there. So Zeno doesn't quite make it to the doors of truth or false.
Think of it like that.
And no one's out of here.
No, that's not the one.
No, there's no way.
I'm not sure you understand the paradox.
I understand.
State the paradox for me, Miss John.
But like, you know that you can walk through a door, but then if you cut it in half, then you would never actually get there. So
Not just in half,
you kept cutting it in half and then a quarter, and then
right? And writing your trip as a sum of an infinite series.
you're getting half of it.
But now, you're talking about a limit. Is the limit the answer we're looking for? How do we deal with the sum of an infinite series? Because to stop anywhere in this process is to not get to the door. But remember, Zeno wants to subdivide this into an infinite sum. It's kind of like when we write a third. A third, that's easy to conceptualize. 1/3, one part out of 3. But when we put it on the real number line, and we insist on writing it as a decimal, what happens? We'll get to that. 1/3 then is written as 0.3. 0.3 Brepton. In other words, you have to write 1/3 to get it as a decimal as an infinite sum. 0.3 Repton is 3/10 and 300ths and 3,000ths and 3/10,000ths and so forth. To leave any of those off and just say the 12 threes on my calculator, no, that's not a third. It has to be the infinite series in order to equal a third. And so it's kind of like what's going on in Zeno's paradox here. Now, he still has an issue here. So we're going to show that this infinite sum does add up to 1. But what about the other aspect of his paradox? That he's saying it's an infinite collection of finite bits of time that implies an infinite amount of time, correct? But what's happening to those finite bits of time? They're getting smaller and what we call infinitesimally small. And as a result then, we can come up with a convergent sum. Right, so you can't really say, okay, the first bit of time took half a second, second took a quarter of a second. And so yeah, you're adding up an infinite collection of finite bits of time, but it turns out it doesn't make an infinite amount of time. It'll make the 1 second it takes to cross that. Alright. That's just some of the philosophy. Zeno is a philosopher. He's showing them the doors to truth and falsity. He's got some followers, okay?
I understand what's going on.
Then look up the fresco in the library of El Escorial.
I read that. Oh,
Okay. How do we analyze this infinite sum? So we're going to look at the sequence of partial sums. S sub n is a partial sum. Big S we're going to use to represent the infinite sum. If we don't put a subscript on it, that means we want the sum of the whole series, the whole infinite series. But if we put a subscript on it, that means you're going to stop at some point. So the sum of the first one is a half. S sub 1 is always equal to T sub 1. But S sub 2 is the sum of the first two, and you get 3/4. S sub 3 is the sum of the first three, and we'll get 7/8. S sub 4, 15/16. S sub 5, 31/32. None of these are equal to 1.
That's a tree.
But can you think of a formula for S sub n?
Well, I don't know, but the numerator, like, it doubles and then you add one, and the denominator.
Or subtract one,
doubles.
right. So you're thinking of a recursive idea of taking the denominator from before. Can you also think of it as what is the bottom of the fraction in each case?
Last
Oh, it's a
number.
multiple of 2.
Yeah, it's power of 2. Power of 2. 2 to the n, okay? And as you were saying, Tiva, the top is always one less than that. Now, we'll actually prove this in a bit, that you do get that. So that's a formula for the nth partial sum. But that's not what the infinite sum is. Here's our formal definition of what an infinite sum is. It's the limit of the sequence of partial sums. So S, when I don't put a subscript on this, means the limit as n goes to infinity of S sub n. It's a tricky concept because this infinite sum is hard to conceptualize. It troubles Zeno so much, right? But we're going to look at the limit of a process. Quite. So in our last example, we're going to say all this is equal to 1 because the sequence of partial sums has a limit of 1. So you see what we're saying here? S equals 1 because the limit as n goes to infinity of S sub n's is equal to 1. And these are the sequence of partial sums. Now, I'm not trying to say that there's some sum out there that equals 1, that there's some partial sum that equals 1. None of the partial sums equals 1. Just like if you took 0.3 and tried to do a third by just writing down 12 threes after the decimal point, that would not equal a third. You have to put the 0.3 replicate down to represent the infinite sum. And that infinite sum is the third. So if the sequence of partial sums has a finite limit S, then the infinite series is said to
Hangman.
converge. Converge. We didn't need hangman. We talked about this term before. If a limit converges, so the sequence of a finite limit S, an infinite sum is only really going to exist if your sequence of partial sums converges on a limit and has a limit. If the sequence of partial sum approaches infinity or has no finite limit, then the infinite series is said to diverge. There you go. Now, sum of an infinite geometric series. We talked about this before, that we can get the sequence to approach 0 if the absolute value of r is less than 1. And as a result, then, we can get the whole series to converge on an infinite sum if the common ratio is less than 1. This will force each subsequent term in the geometric series to be smaller. And so you keep on adding less and less. And in the case of geometric series, this will always guarantee an infinite sum. Do you remember that formula? It's actually a lot simpler than the old one. Here, let's compare it. Remember this formula? The partial sum of a geometric? S sub n. Remember your S sub n formula? I'm going to tell us the other day you want a good time to get these all memorized. Remember what you said there? ASAP. Okay?
T sub 1, parentheses 1
T sub 1.
parentheses 1 minus n.
No. And all over 1 minus r. Okay? That's probably the most complicated formula for the section. And we turn it now to the easiest formula for the section. Because we talked about this limit. If the infinite sum, let's back up. It's the end of the page. The infinite sum is the limit as n goes to infinity of s sub n. It's the limit as n goes to infinity of t sub 1 times 1 minus r to the n all over 1 minus r. N is the only thing changing. What's going to happen to this term right here? This will approach 0 if absolute value of r. If the absolute value of r is less than 1. That was our condition for r to the n. R to the n goes to 0 if you've got a common ratio that's less than 1, between negative 1 and 1. So notice how that's going to greatly simplify the formula now. So now your formula is just what? Or just 1 minus, over 1 minus r.
Yeah.
T sub 1 over 1 minus r. Okay? Easiest formula. So we go from the hardest formula, if you're doing the sum of the first n terms of the geometric series, to now we're doing the infinite sum of the whole geometric series. Now remember there's a condition on this. It only applies if the absolute value of r is less than 1. Right? If basically the series, the sequence of terms is getting smaller, then the sequence of partial sums will converge on the infinite sum. So notice if absolute value of r is greater than or equal to 1 and t1 is not equal to 0, then the infinite geometric series diverges. Okay. Now, proof. I just did the proof. Sorry, I didn't realize I put a little thing here for the proof later on. The proof is what I just put on that previous page, okay? Just did. Maybe I'll remember that next time for next class, that I got the proof right after, okay? And just to start off the proof, this is the limit as n goes to infinity of s sub n. And that formula is t sub 1 times 1 minus r. Find the sum of the infinite geometric series 9 minus 6 plus 4. Well, it tells you it's infinite geometric. We have to look at the common ratio first, though. Negative 6 ninths, which is negative 2/3. Absolute value of r is less than 1. Check. That's supposed to be a 1. So we can use it. So the infinite sum will be t sub 1 over 1 minus r. 9 all over 1 minus a negative 2/3. 9 over 1 plus 2/3. So let's multiply top and bottom by 3 to get rid of the secondary fractions. 27 over 3 plus 2, 27 fifths. Now, can we do our little check on the T99 check? How do you do this on the T99? I have one up here. This is something. Check. Now, are you adding up just what it says there? 9 minus 6 plus 4, and it's kind of hard to measure the next term, so you want to do something else, right?
Yeah.
You gotta do the
You want to do the sigma
sigma
notation.
thing, the infinity thing.
9
No, what do we need first in sigma notation?
Well, you need the formula.
A formula.
And then the variable.
9,
times
Then the
negative
1
nines. Negative 2 divided by 3. Get that in parentheses because we want it to alternate in sign, so you got to make sure the negative is inside the base. Raised to the
x minus 1.
x minus 1. X going from 1 to infinity. See if it lets you put infinity in there. I hope so.
27.
And it says 27.
Oh, or
Okay. Alright. You could have also done this with your limit command.
I don't know.
Oh, no.
Well,
Limit.
it was the sum of the n thing.
Limit, and then put in this thing again. Again, is this going to work? Yeah, the limit of the sum of 9 times negative 2/3 to the x. It's supposed to be x minus 1, right?
Yeah.
That's a little clearer. X minus 1 for x going from 1 to n, parentheses,
X.
I'm using x here because I'm using x for adding up all the terms from 1 up to n. And then, comma, n going to infinity.
oh, it worked.
This is using the idea of defining an infinite sum as the limit as n goes to infinity of the partial sums.
Hey, that's good.
So note the difference there, and I think the calculator handles both.
Yep.
So in this one, I'm essentially doing the infinite sum s right away by telling the calculator, make your final term infinity, or the final index infinity. On this one, I'm asking the calculator to do the limit as n goes to infinity of the partial sums. So all of this inside here is just s sub n, and then we let n go to infinity. Okay. I show you this because sometimes the calculator has issues with you putting in infinity in one of these two. Not in this case, but now you can see how you can think of the infinite sum in two ways, right? Okay. Now, for what values of x does the following infinite series converge? What kind of series is this? Geometric. And what's the common ratio then? X minus 2. You keep multiplying by x minus 2. That's what you have to do that. And a little more than that though. To get the series to converge, r must be less than 1. More specifically, absolute value of r must be less than 1. So that means absolute value of x minus 2 must be less than 1. And here's where you're real speedy with the...
One between 1 and 2.
Yeah, put x minus 2 in between, negative 1 and 1. Add a 2 to all three parts. And there's your interval of convergence. It is called the interval of convergence. If x is in that range, the series will converge. If it's outside that range, it won't. Okay? All right. The infinite repeating decimal, 0.45, can be written as an infinite series, 0.45 plus 0.045 plus 0.045. What is the sum of this series?
0.45.
Not 1 over 100.
Isn't it 0.45?
See, maybe you taught a little trick on this in middle school. Do you remember it? I taught you in algebra. Remember it? Fine. We'll try that later. Let's just start with the infinite sum. This is geometric, right? It's geometric. The first term is 0.45. What's the common ratio? 0.01, 100th. 0.01. So the infinite sum should be t sub 1 over 1 minus r. So you get 0.45 over 1 minus 0.01, or 0.45 over 0.99, 45/99. You can take out a 9 and you get 5/11. Now you can just check 5/11 on your calculator real quick. Get the star equal to it. It says the 11s are kind of neat that way. They keep on repeating 2 digits and they all add up to 9. What's 1/11? I'd say 0.09. 1/11, a little less than 1/10. 1/10 is 0.1. 1/11 then is 0.09. So it's 0.909090.
Oh, one of them. No.
10.
Oh, 0.9. Oh.
Can't you just figure that out right away?
How?
Because it's just like adding.
Adding what?
Like you add the first three, then just go with the rest.
You can add the first 3 terms here and get what? If it stops here, you don't get 5/11ths.
But it's gonna go on forever.
Yes, that's right.
So you just know it's more platform. Yeah, you just know what it's gonna be. That I know. Because it's just forever.
It is repeated forever, and we use that so we can use our infinite sum formula. Maybe you're talking about this technique. Are you ready? Here's an alternate approach. If we let n equal 0.45 repetent, then 100n is 45.45 repetent. As we move the decimal place over to, right? And then we can subtract these two. 100n minus n should equal 45.45 repetent minus 0.45 repetent. So we get 99n equals 45, so n equals 45/99. And again, you get 5/11ths. I thought maybe you were showing that in middle school, a little trick.
You just multiply by enough to get all of the repeating stuff
Right,
over.
split over, and then subtract, and then you have all that things to
Could
cancel.
you do 10 and as well? And then...
Then you remove.
Oh, that's
If you use
what
10, it
I'm
wouldn't
thinking.
quite,
Oh,
they wouldn't cancel out right.
You could just like identify that as 5 elements. Do that.
Hmm?
If that was like on a test, could you just like identify that as 5 elements immediately?
Because you got those memorized. Do you know your sevenths too?
No, 7 13.
That's a 0.42.
Those are pretty cool. They repeat 6 digits.
I know my thirds.
That's good. That's good. It's good you know your thirds,
I know.
because that's where we're coming up here. Joey says he knows his thirds. So now we're going to do the Charlie Brown wishy-washy approach. Recall how
There he is.
Zeno's infinite series, a half plus a fourth plus an eighth plus a 16th, remember? That added up to what?
Almost 1.
Let's check that. Let's check that with our formulas now. Not almost 1. The infinite sum is 1. The infinite sum, t sub 1 over 1 minus r, 1/2 over, what's the common ratio here? 1/2. So you get half over half, you get 1. Now, here's Charlie Brown's wishy-washy journey. This is how you can cut things into thirds. Are you ready to try it?
Yeah.
Okay, I need a helper. Michelle?
Oh, is this where you want to have?
I'm going to move Charlie Brown, and you mark down where he ends up, okay?
Oh, yeah. That's done.
Yes, you just mark with a pen.
Especially if you have.
Easy to
Class, you help me step aside so everybody can see. Let me know when you think Charlie Brown is halfway to the Halloween party.
He's halfway. Back.
I got it.
Right about there?
Yeah, that's good.
Is that good?
No,
I mean, you in the back room should read it all the time.
We're gonna need
Good?
you, GeoGebra, for this.
Okay, make a mark there. Okay, now
Make your mark later.
he gets to the party and realizes, I have no costume.
Oh.
I better back up and go back. And he gets halfway back this way. So it's not Zeno's journey, is it? Zeno would have kept having the target in mind and kept going to the Halloween party. Even though he would have subdivided into an infinite sum of finite at a time and never gotten there.
The Romans never celebrated Halloween.
Does that look halfway back?
I know, but that's what
Okay, mark that. Okay, now Charlie Brown realizes, wait, I've got the perfect costume. It's a Charlie Brown costume. I'm gonna go to that party.
You can't get in without a
Stop about there. Okay, mark that. Mark that.
Wait, why do you stop this time?
Why stop this time? You realize, wait, I'm Charlie Brown.
No, you have to use it. It's
It's not gonna work. I'm gonna go back and get a fake ID. So,
Stop.
right about there. Okay.
Oh god, he's gonna get stuck first.
Yeah. Okay.
Walled in.
So he's got his fake ID. Well, no, he doesn't get his fake ID because before he can get home, he realizes
There's
that would be unethical. I'm just going to go there and be myself.
Stop.
Charlie Brown.
Oh, no.
What? You see, you keep picking up the pen too early and then think, what? Charlie, come on. Right about there. Okay. Okay. Good. Okay. They says myself is not good enough for most of the crowd.
Oh wait,
Lucy's gonna make fun of me.
just gonna move that football.
What is it?
You're good.
You know, there, right about there. You'd say okay. Okay. Now, can you finish up the rest of the route for us here? Now go to the right, half of what's left there. Oh wow, what happened? There you go. We're about there, okay? Now let's make it big. So did that roughly cut things in a third?
Yeah.
Would you say that's about a third?
Yeah.
Now how can you get the 2/3 point?
Oh, wait, hold on.
Thank you, Michelle. How can you get the 2/3 point?
On the other side.
Let's check with our ruler. Mr. Lang, if you had that all along, why didn't you show it?
Trying
Oh,
to simplify it.
there you go. There. Oh gosh.
Are we way off?
Oh no, my ruler's a little off. Yeah, my ruler's a little off. What happened? We went halfway there, right? Half. Oh no, see now we're more like here. Yeah, why I lost track of where she was. Halfway there, a quarter back, and see this would be a half then, and then boom, boom, boom. Yeah, it's right here. Charlie Brown, get it together. Okay, there you go. That's a third of the way. I think at one point maybe you went the wrong way. Okay, now let's see how this works. The series is a half. What's the next term?
Multiplied by the negative.
A quarter.
Negative a fourth.
Minus a fourth,
Minus a fourth.
plus an eighth, minus a 16th, plus dot. So your first term is a half. The common ratio,
Oh,
negative 1/2.
Oh, yeah.
So that changes the infinite sum slightly. Now you get a half over 1 minus negative a half. A half over 3 halves. And there's your 1/3. Okay. So now you know how to cut things into thirds. It's kind of hard for us. We're used to the symmetry. You get dressed in the morning. You don't put like a third of your hair over here, right? Oh my gosh. Okay, someone's stupid. Okay. And then 2/3 of your hair over here. Kind of like that symmetry look, right? All right. Okay. Come around, see how you're doing on various stuff.